Yes. This is the last section in chapter 10 of our biggest unit. It's going to be your easiest section. But the one thing that I have to point out to you is that there are some things that you will be shown or given, and you're supposed to remember them from Math 1. Now, some of you took Math 1 last year, or Advanced Math 8 last year, and you may not remember this. So I'm just going to start off with what you are supposed to remember from either last year's math class, or depends when you took Math 1 or Advanced Math 8 or something like that. These are linear graphs. They form lines. These are the quadratics. That's what Chapter 10 is all about. Chapter 10 has been all about these kinds of graphs, either opening upwards or downwards. And then the other Math 1 we talked about in Unit 0 in Math 1 was this exponential graph. This graph that gets increasingly bigger or decreasingly smaller without ever touching that x-axis. Okay? So your job will be to know the difference between this graph and this graph and this graph. This is going to show up on the SBAC for those of you who are juniors, by the way. The first way that you learned it in Math 1 was through the graph. But we're not going to do that in Math 2. In Math 2, you're going to have to know it based off of the equation, and you're going to have to know it based off of a table primarily. So let me show you some things. First and foremost, linear functions have just an x in it. Y equals x. They have a common difference between their y coordinates, means it goes up by the same amount. It has a rise over run. A rise over run that is the same all the way down the line. Quadratic functions have a variable x squared in it. They have a second differences between their y coordinates. I'm going to talk about what that looks like with this picture down below. Lastly, exponential functions have a variable x in the exponent. They have a common ratio, not a difference, a ratio. Ratio means multiplication between their y coordinates. So, you have this somewhere in your notes. I believe it's on the right-hand side of your column. It might be the second thing that's down below your graphs. That's what I'm looking at right now. Here's what it says. When the x values in a set of data pairs have a common difference, you can analyze the data numerically to find the best model. If you look at this table, let me zoom in on it real quick. We're going... our x values are getting one bigger and one bigger and one bigger. Our y values, we're adding 3 and adding 3 and adding 3. If they have a common difference of 3, meaning we're adding 3 every single time, this is the same thing as a rate of change of 3 over 1, 3 over 1, 3 over 1. The same common difference means it is linear. Fill that in on your notes page. Right there, right-hand side. This is what you're writing down. The second one says, we're adding 1, adding 1, adding 1. When we look at the pattern, we went from 0.25 to 0.5 to 1 to 2, and we look at that and we say, hey, it's multiplying by 2, multiplying by 2, multiplying by 2. If it's multiplying by the same number every single time, it is called a common ratio. Common ratios are exponential. Write that in.
Wasn't the other one multiplying by the same numbers?
Was it multiplying or was it adding? So adding and subtracting is a common difference. Multiplying or even dividing is a common ratio. And so the last one, sometimes what's going to happen is this. You start looking at seeing if you're multiplying by the same thing. It doesn't multiply by the same thing. And so you subtract 2. And you go, I'm adding 2 now. Now I'm adding 6. Now I'm adding 10. You have to check not just the difference, the first difference. Sometimes you have to check to see if there's a pattern in the second differences. What's the difference between the -2 and the +2? They added 4. Going from the 2 to the 6, they added 4. Going from the 6 to the 10, they added 4. That's a second difference. Which second differences are quadratics. Now I have to say that these three things that you have just written down, you check to see, are you adding and subtracting the same amount? If it is, linear. If it's multiplying by the same amount, yes, it's exponential. You have to check the tricky ones. If you're adding different amounts, is the second difference the same? If it is, it's quadratic. If it's not, or if there is no pattern, there is a choice that says neither on your worksheets. So keep in mind, it will either fit this, or if it doesn't fit any of these things, choose neither. Now, I don't know if you have this one in your notes. So, at this point in time, you will probably have to go away from, because I don't think you have the one that says -211, -150315. Do you have that anywhere in your paper?
Yeah.
In the notes paper? Not in the notes paper, right? So it's in the packet. Go ahead now, switch over to the packet. You are done with your notes portion. You're going to your packet now. And I think this is under worksheet 9, the second page, number 3. This is worksheet 9, the second one, number 3. Here's what the directions say. Graph each set of points. Which model is appropriate? Choose linear, quadratic, or exponential. They give you 4 points. -211, -1503, 15. Just to review, I like to go like this. 0, 1, 2, -1, -2. I think that'll handle all of my x's. I also like to count out my y's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think I have to go to 11 anyways. So I like to number my axes. It helps. And then I'm going to start plotting my points. Here's my first point, which is right here. Put a big dot. Here's my second point. Here. Put a dot. Remember, X is horizontal, Y is vertical. That's why I'm going to the left 2, up 11. To the left 1, up 5. Then I do my third point, 0, 3. 0 for your X, 3 for your Y. And then 1, 5. You have 4 points. And the first thing I can say, it's not linear because I can't go through every single point. It's not exponential because I'm not going through every single point. So is there another thing that I can do? Maybe I can do something like this.
Yes.
What kind of graph is that? That's what you write. So you plot it, and then you write down what you think it is, which, wait, I know it is a quadratic. Perfect. First kind of example, taking points, graphing them, picking which type it is. Pretty simple. Second example is what happens when they give you a table. You have to make your decision based off of common difference, common ratio, or second differences, or neither. Here's what it says. Which type of function best models the data in each table? Choose from linear, quadratic, exponential, or neither. Hint, use differences or ratios. So they're going up by 1, up by 1, up by 1, up by 1 for the x's. That usually doesn't make a difference. Let's check the y values. What's happening? What's happening? What's happening? What's happening? What's the pattern? What are they doing to go from one number to the next number to the next number to the next number?
Times 2.
Times 2, times 2, times 2, times 2. But wait, Mr. Problem, I'm adding 3 and then I'm adding 6 and then well, look to see if the pattern is adding the same thing or maybe it's multiplying like this. It is multiplying by 2. That's a common ratio. What type of function is it? If it's a common ratio. There it is. Keep in mind, common differences, linear. Common ratios, exponential. Or second differences are quadratic. And if it doesn't fit any of those 3 patterns, keep in mind there is the tricky choice. We're going to throw in 1 or 2 that just don't match. Neither is a possibility. We'll stop right there.